Good morning all. In continuation to our discussion on nonlinear transformation based image enhancement techniques, today we will discuss power law transformation. The general mathematical equation of power law transformation, it is given over here. It is S equals to C R to the power gamma, where R is my input intensity level, S is my output intensity level, C and gamma are my constant. Now, depending upon the value of gamma, the power law transformation can be further subdivided into three broad categories. Case 1 when gamma is greater than 1, case 2 when gamma is less than 1, and case 3 when gamma equals to 1. So in this discussion, we will discuss the case 1, that is when gamma is greater than 1. The algorithm of power law transformation, it is written over here. In step 1, first we have to consider the unnormalized input intensity range R. In step 2, we have to convert this unnormalized input intensity range R into normalized input intensity range Rn. In step 3, we will perform the power law transformation, and in step 3, we will get the normalized output intensity range Sn. And in last step, that is in step 4, we will convert normalized output intensity range Sn into unnormalized output intensity range S. So in order to understand the power law transformation, let us take the example of an 8-bit image. So for an 8-bit image, n is equals to 8. If n equals to 8, the number of gray label L equals to 2 to the power 8, that is equals to 256 number of gray labels. Now their representation in digital image, it starts with the minimum gray label 0 to the maximum gray label 255. So for an 8-bit digital input image, the intensity of gray label in a digital image, it varies from 0 to 255, or in other words, we can say for an 8-bit digital input image, the unnormalized input intensity range R, it varies from 0 to 255. So for an 8-bit digital input image, we have identified the range of unnormalized input intensity, which varies from 0 to 255, or in other words, for an 8-bit digital input image, this unnormalized input intensity range R, it varies from 0 to 255, and we want our output intensity range S. Our unnormalized output intensity range S will also vary from 0 to 255. Now in step 2, we have to convert this unnormalized input intensity range R into normalized input intensity range Rn, and for the same we will perform a simple mathematical operation, that is Rn equals to R divided by 255, that is each intensity value in this unnormalized range will be normalized with respect to its maximum intensity value, that is 255, and if you apply this mathematical equation, the range of Rn we will obtain first the minimum value. The minimum value of R, it is 0. If you normalize this intensity value 0 with respect to its maximum intensity value 255, that is 0 divided by 255, it becomes equals to 0. Next, for the maximum value of R, the maximum value of R, it is 255. If you normalize this intensity value 255 with respect to its maximum intensity value 255, that is 255 divided by 255, it becomes equals to 1. So normalized input intensity range Rn will vary from 0 to 1, and we want our normalized output intensity range Sn will also vary from 0 to 1. Next, on this normalized input intensity range Rn, and normalized output intensity range Sn, we will perform the power law transformation. We have just studied the general equation of power law transformation. It is S equals to C R to the power gamma. So applying power law transformation on this normalized input intensity range Rn and normalized output intensity range Sn, we can write Sn equals to C into Rn to the power gamma. Now in order to understand the power law transformation for gamma greater than 1, here we have to assume some value of gamma. So for simplicity, let us assume gamma equals to 2.5. Now in this equation of Sn, we will substitute the value of gamma in order to explore the power law transformation for gamma greater than 1. So in this equation of Sn, we will substitute the gamma equals to 2.5. So the equation of Sn, it becomes Sn equals to C Rn to the power 2.5. Now in this equation of Sn, we have to determine the value of this constant C, and for the same we will apply the boundary condition. When Rn equals to 1, Sn is also equals to 1. So in this equation of Sn, in order to determine the value of C, in place of Sn I will substitute 1, in place of Rn I will substitute 1, and we will determine the value of this constant C. So substituting Sn equals to 1, the equation becomes Sn equals to 1 equals to C into, in place of Rn I will substitute 1, so 1 into 1 to the power 2.5. So if you solve this expression, you will get the value of constant C, it is equals to 1. Now substituting C equals to 1 in this equation, and we will determine the relationship between Sn and Rn. So in this equation, we will substitute the value C is equals to 1. So the equation of Sn, it becomes Sn equals to 1 into Rn to the power 2.5. And in the last step, we have to convert this normalized output intensity range Sn into unnormalized output intensity range S, and for the same we will perform the simple mathematical equation, that is S equals to Sn into 255. Next, we will do the plotting. Similar to the previous, along x-axis we will take our input intensity range R. Along y-axis we will take the output intensity S. Now first I will mark the critical point along x-axis. This is our origin. First critical point, it is L by 4. Next one, it is L by 2. Next one, it is 3L by 4. And this is our L minus 1. Similarly, we will mark the critical point along y-axis. This critical point, it is L by 4. This is L by 2. This one is 3L by 4. And lastly, this one, it is L minus 1. So for an 8-bit digital input image, if n is equals to 8, L is equals to 2 to the power 8, that is equals to 256. So if L is equals to 256, L by 4, it is equals to 64. L by 2, it is equals to 128. 3L by 4, it is equals to 192. And L minus 1, it is equals to 255. Similarly, we will write along y-axis L by 4. If L is equals to 256, L by 4, it is 64. L by 2, it is 128. 3L by 4 it is 192 and L minus 1 it is 255. Next we will draw a simple table. In the first column we will write our input intensity range, unnormalized input intensity range R. First point it is 0. Next it is L by 4. If for an 8-bit image n is equals to 8, L is equals to 256 and L by 4 it is equals to 64. L by 2 it is equals to 128. 3L by 4 it is 192 and lastly L minus 1 that is 255. Next we will convert this unnormalized input intensity value R into normalized input intensity value Rn, and for the same we will perform the simple mathematical equation Rn is equals to R divided by 255. So one by one we will normalize all these intensity values. First, when R is equals to 0, so if we normalize this intensity value R is equals to 0, that is 0 divided by 255. If you simplify this, you will get the output is equals to 0. Next, we will normalize this input intensity value 64 with respect to its maximum intensity value 255. So it is 64 divided by 255. If you solve this, you will get 0.250, and if you approximate it up to 2 decimal place, it is equals to 0.25. Next, we will normalize this intensity value 128, and for the same in this equation of Rn, in place of R I will substitute 128. So the equation becomes 128 divided by 255. If you solve this, you will get 0.501, and if you approximate it up to 2 decimal place, it becomes 0.50. Similarly, we will normalize this intensity value 192, and for the same in this equation of Rn, in place of R I will substitute 192. So it becomes 192 divided by 255. If you solve this expression, you will get it is 0.752, and if you approximate this number up to 2 decimal place, it is approximated to 0.75. Finally, we will normalize this intensity value 255, and for the same in this equation of Rn, in place of R I will substitute 255. So the value of Rn we will obtain, it is 255 divided by 255, it is equals to 1. Now on these normalized input intensity values, we will perform the power law transformation. The equation of power law transformation that we obtained earlier, it was Sn equals to 1 into Rn to the power 2.5. Now one by one on these normalized input intensity values, we will perform the power law transformation. First, when Rn is equals to 0, we will determine the value of Sn. For the same in this equation of Sn, in place of Rn I will substitute 0. So it is 0 to the power 2.5, that is equals to 0. Next, when Rn equals to 0.25, we will determine the value of Sn, and for the same in this equation of Sn, in place of Rn we will substitute 0.25. So the value of Sn we will obtain, it is 1 into 0.25 to the power 2.5. If you solve this expression, you will get 0.031, and if you approximate it up to 2 decimal place, it is equals to 0.03. Next, when Rn is equals to 0.5, we will determine the value of Sn. And for the same, in this equation of Sn, in place of Rn, we will substitute 0.5. So the equation of Sn, it becomes 1 into 0.5 to the power 2.5. If you solve this expression, you will get 0.176, and if you approximate this number up to 2 decimal place, it becomes equals to 0.18. Next, when Rn equals to 0.75, we will determine the value of Sn, and for the same, in this equation of Sn, in place of Rn, we will substitute the value 0.75. So it is 1 into 0.75 to the power 2.5. If you solve this expression, you will get the value, it is 0.487, and if you approximate it up to 2 decimal place, it becomes equals to 0.49. And lastly, when Rn equals to 1, we will determine the value of Sn, and for the same, in this equation of Sn, in place of Rn, we will substitute the value 1. So the equation of Sn, it becomes 1 into 1 to the power 2.5. So if you solve this expression, you will get it is equals to 1. So we have obtained the normalized output intensity values Sn, and finally we will convert these normalized output intensity values Sn into unnormalized output intensity value S by performing the simple mathematical operation S equals to Sn into 255. So one by one, for each value of Sn, we will perform this unnormalization operation, or in other words, for each value of Sn, we will determine the value of S. First, when Sn equals to 0, in order to determine the value of S, in this equation of S, in place of Sn, I will substitute 0. So if I do the substitution, I will get the expression 0 into 255, and if you solve this expression, you will get the value that is equals to 0. Next, when Sn equals to 0.03, we will determine the value of S, and for the same, in this equation of S, in place of Sn, I will substitute the value 0.03. So the equation of S, it becomes 0.03 into 255. Now if you solve this expression, you will get the number 7.65. Next, we will round off this floating point number to its nearest integer number. 7.65, its nearest integer number, it is 8. Next, when Sn equals to 0.18, we will determine the value of S, and for the same, in this equation of S, in place of Sn, I will substitute 0.18. So the equation of S, it becomes 0.18 into 255. If you solve this expression, you will get the number, it is equals to 45.9. Next, we will round off this floating point number to its nearest integer number. So 45.9, its nearest integer number, it is 46. Next, when Sn equals to 0.49, we will determine the value of S, and for the same, in this equation of S, in place of Sn, we will substitute 0.49. If you do the substitution, you will get the equation of S as 0.49 multiplied with 255. If you solve this expression, you will get the number 124.95. Next, we will round off this floating point number to its nearest integer number. 124.95, its nearest integer number, it is 125. And lastly, for Sn equals to 1, we will determine the value of S, and for the same, in this equation of S, In place of Sn, we will substitute the value that is equals to 1. So the equation becomes 1 into 255. If you solve this expression, you will get the number. It is equals to 255. Next, we will do the plotting. So first point we will mark when r equals to 0, s is also equals to 0. So when r equals to 0, s equals to 0, it represents the origin. Next, when r equals to 64, s equals to 8. When r equals to 64, s equals to 8, very close to this, tentatively representing this point. Next, when r equals to 128, s equals to 46. When r equals to 128, s equals to 46, little bit closer to this line, little bit closer to this point L by 4, tentatively representing this point. Next, when r equals to 192, s equals to 125. When r equals to 192, s equals to 125, very closer to this point L by 2, tentatively representing this point. And lastly, when r equals to 255, s is also equals to 255. So when r equals to 255, s is also equals to 255, tentatively representing this point. Now we will connect all these points. So this represents the power law transformation characteristics plot when gamma equals to 2.5. So this is the characteristics of power law transformation. When we have considered the gamma value, it is equals to 2.5, and in this case we have obtained the value of the constant c, it is equals to 1. Now let us analyze this characteristics plot. So in the input side, when the intensity value is changes from 0 to 64, in the output side, the change in the intensity value, it is very small. You can observe in the tabular plot also, you can observe in this table also, when r varies from 0 to 64, in the input side, my difference is 64, but in the output side, the difference in s, it varies from 0 to 8. So the difference here, it is only 8. So input side, my difference is 64, but in output side, my difference is only 8. And this range 0 to 64, it is my dark range. So in this power law transformation, when I have considered gamma value, it is 2.5, I am compressing my dark pixel. So here we compress the dark pixel values. Now look at in the bright side, when my input intensity value R, it varies from 192 to 255. This is my bright region. In the input side, I am varying from intensity value 192 to 255. This range is very small, but look at in the output, Look at the change in the output intensity value S. The difference here it is very large compared to that of my input. In the table also you can see in the bright side when R varies from 192 to 255, the difference here it is 63. And look at in the output intensity value S, when R varies from 192 to 255, the S varies from 125 to 255. So the difference in the output intensity value it is 130. So in the bright side, for bright pixel values, when R varies from 192 to 255, the difference in the input it is 63, and the difference in the output intensity value it is 130. So here I am expanding my bright pixel values. So it expands the bright pixel values. Since in this power law transformation, when I have considered the case gamma greater than 1, and I have considered for a particular value of gamma that is equal to 2.5, in the transformation characteristics, I am compressing my dark pixel values, expanding my bright pixel values, and as a result, we will obtain a dark image output. Representing on a digital input image, if I perform this power law transformation for gamma greater than 1 in the output image, it is darker compared to that of my input image. So in power law transformation, we are discussing about the case study when gamma is greater than 1. Once again, the general equation of power law transformation, it is S equals to C R to the power gamma, where R is my input intensity level, S is my output intensity level, C and gamma are the constant, and just now we have plotted the transformation curve for gamma value equals to 2.5. The value of the constant C we have obtained, it was 1. Similar kind of power law transformation characteristics for gamma equals to 2.5, it is represented using this nonlinear characteristics in our reference book also, and the value of the constant C, it is considered to be 1. This is a small project work I made it in MATLAB in order to demonstrate power law transformation for gamma greater than 1. So input image A, it is my input image. In order to perform power law transformation on this image A, first I make it normalized. In MATLAB, in order to make the image normalized, we have to use the inbuilt function im2double. Now on this normalized image ID, I have performed the power law transformation considering the value of C, it is 1, and the gamma value I have taken, it is 2.5, and as a result I am obtained and darker image output. And finally this normalized output image out D, I have to denormalize it by using this MATLAB inbuilt function, that is im2 unsigned integer 8, im2 ui98, and as a result I obtained my final output image out. You can observe in histogram plot also, original image A, it's a 8-bit image, and for an 8-bit image, the input unnormalized input intensity range, it varies from 0 to 255. When I make it normalized, when I make this image a normalized by using the MATLAB inbuilt function im2double, the normalized input intensity range Rn, it varies from 0 to 1. On this normalized input image ID, when I perform the power law transformation, the histogram of my normalized output image out D, it is shifted towards the darker side, it is shifted towards the left side, and as a result I obtain a darker image output. The histogram of normalized output image out D, it varies from 0 to 1. And finally, when I make this out D image unsigned integer 8 format, that is, when I make this out D image back into 8-bit image, my output image intensity level, it also varies from 0 to 255. Another trend that we can observe in this transformation characteristics, consider the transformation curve of gamma value, it is equals to 2.5, gamma value it is equals to 5.0, and so on. So as the gamma value increases, this curve is shifting in this direction, representing we are expanding our bright region more and more. So as we are increasing the gamma values from 2.5, 5.0, 10 and 25, gradually our curve is shifting towards the right direction, and as a result we will get a darker image output. So the conclusion here, if the gamma value increases, our image becomes darker and darker. So this is an example which is given in the book. This is the original image, and on this original image power law transformation has been performed for gamma equals to 3.0, for gamma equals to 4.0, and for gamma equals to 5.0. And as the gamma value increases, you can see the output image, it becomes darker, darker and darker. So today I am going to stop here. If you have any suggestions, if you have any doubt, you can write it in the comment section, or you can write email to me. Till then, happy learning, have a good day, and thank you all.